welcome back. This is a series on the mechanics of the sum of divisors function. Previous video, I did a little introduction onto how we got here and why I'm doing this video. So before we continue though, I would like to do two things. I'd like to talk about, present keywords and the approach. I think this is going to be important because it's going to be helpful in understanding where I'm going and why I'm taking the route that I'm taking. So I hope that this allows people to understand how I'm approaching the examining the sum of divisors function. Because as I presented in the previous video, I effectively did my own independent study of the sum of divisors function from the beginning, from scratch, as my channel states ab initio, right, from the beginning. So here we are, and the first thing I want to present, and I'm going to try to keep these up on the board the entire time, is keywords that I want everyone to be aware of and think about as we're going through this. And it's going to be in kind of sets here. So we've got, I want to think about traits, characteristics, no, that's correct. Sticks, behaviors, functions, roles, properties, and attributes. All right, we'll be talking about things a lot. So that's the first set of words. And basically what I'm doing is I'm basically presenting the same concept, just with a lot of related words, right? So words associative. So it's kind of a practice of associative thinking, right? So these are all words that are kind of related to each other and kind of, as you can tell, have a theme. Then we have definitions, because traits are, well, defined by definitions, right? Which are basically set up our perspective. It is our understanding. Sets up our parameters, another way of thinking about it. Context. Now, definitions are by their very nature explicit, right? That is, they are direct, obvious, stated. So, we can talk about that. Now, there's also, within each definition, we have limitations. As soon as we define what something can be, we're also defining what it can't be, right? So there's a relationship here, limitations, restrictions, or my favorite, constraints. What are our constraints? Right? Favorite question of mine. Now, a lot of times, once we've established the definition and therefore the explicit ideas, the direct, obvious, stated ones, then the limitations, restrictions, and constraints are not necessarily explicit. They're not necessarily obvious. And so the idea behind this is these are sometimes, not all the time, but oftentimes, I would say, implicit. That is hidden. Unknown. We don't know what we don't know. And so they are, another way of thinking about these is they are implied, and consequently must be inferred. So I will put that inferred. Finally, I want to talk about the idea of, which we've already presented in the last video. This leads to invalid. The concept and that is going to be super important, critical for us to keep in mind. And the majority of what we will be talking about is what is valid and what is invalid within a certain context. All right? So these are the key words I want to keep in mind. And I'm going to leave some space here because I think there will be others that will come up as we go on, and I want to keep that here. So I'm hoping to be able to use that as a reference as we go on from this. Now, the other thing I want to do is talk a little bit about the approach that we're going to go through this entire series. Because I think if I don't explain it, it's going to be frustrating to some that watch this, and they're going to want to skip ahead, or they're going to want to just get bored and stop altogether, because I am going to be taking it slow. And so I want to talk about the approach real quick, and it is as follows. Approach of investigation or examination of the mechanics of the sum of divisor's function. The reason why I wanted to call this out and have a kind of separate video for this too is I want this to kind of stand out, because this is something that I hope people go back to when they explore their own, decide to investigate, examine something on their own version of the sum of divisors function, right? Whatever it is, when you encounter something that you don't know, that's unfamiliar, I found it extremely helpful to follow a set of steps that lead to new ideas, new understanding, new discoveries, consistently. Now, it doesn't work all the time, and of course there's variance, but as far as I'm concerned, this applies not only to mathematics, but any discipline, really. So the first thing we're going to do is we're going to, and it's really an algorithm, if you will. Step one, we're going to define something, right? Step two, we're going to identify keywords. Within the definition. I'm going to use that to establish a baseline. And by that I mean truly something that you understand, that you know, that is irrefutable. A sort of axiom, if you will, but it's got to be within the context of whatever we're studying, right? So it's not an axiom because we've all established axioms. It's an axiom within the context of what you're studying. Something that you understand and know to be certain and true beyond all doubt, beyond a shadow of doubt, right? And I'm talking you'd be willing to, you're so certain of this that you're willing to put your life on the line. Like, that's how certain we want to be when we establish a baseline. And if you are not that certain, then you've not established a baseline. You established a guess. you don't know, you think, right? And that's the difference, I guess. Like, from thinking to knowing. And we do this, well, how do we really establish a baseline? How would we find it? Well, step 4, simplify. And reduce. Form. In other words, we abstract or remove as much as possible without taking away from our baseline. And this is tricky. This takes practice and this takes time, because a lot of times what happens is people abstract and remove so much that they don't actually have a baseline. They think they do. So this takes trial and error. This is not something that's easy to do. This is difficult. Simplify too much and you're missing context. Oh, as much as possible without losing context. And as we shall see, context is the crux of underpinning the entirety of the sum of the divisor's function, how it works and how it doesn't work, right? We're going to explore both things. And so once we get to step 4, we simplify and reduce. Once we reduce the form, step 5 is, let me see if I can do that here. Step 5. Generate a set of data. Produce results. Now it's tempting when you do this. First of all, what does that really mean? That means run the system, run the function, turn the gears of the system. In our case, it's going to be the sum of divisors function, but this could be an engine, a mechanism, a box that does something, and you spin something, a jack in the box, right? You spin something and something happens, right? And so we can watch it do that. So we generate a set of data, and produce results, right? And we watch what's going to happen. And so the key to this is to be methodical, though you have to do this methodically. Come on. Move this up. Right. And maybe like that. And we're going to do, so we're going to do here, and we're going to do this. This needs to be done methodically, at least at first, and systematically. If you skip around, you establish a baseline, you simplify and reduce form, and then you generate a set of data skipping around, you're likely to miss information, key pieces of information. And this kind of goes back to the abstracting and removing as much as possible, but then also being rigorous. So, right? There's a word for this. Rigorously. And meticulously. Explore a system. At some point, you will want to skip around, but not when you first start. So you have step 5. Now, once you've produced a set of results, you're then going to want to, step 6, organize. results. And I'm gonna actually say organize, arrange, or structure data. This is very important. This is critical because a lot of times the data that you get is, well, looks a little random, and we're going to see that. But as soon as we say, is there a way that we can arrange, organize, structure this data that allows us to understand something? And when we do that, we start seeing patterns. We start seeing things emerge, that implicit ideas, hidden, unknown implications come out. And so once we've done this, we go back to I like to call it step 7. Go back. Go back to step 2. And actually, I'm going to identify or observe. I'm very fond of the Sherlock Holmes series, right? Books, TV shows, movies, you name it, pretty much all of them. And of course, the line, right? One of my favorite lines is, "We see, but we do not observe," right? Might be you see what you do not observe, because I think it's Sherlock Holmes is talking to Watson, right? And so he says, you see what you do not observe. But I'll generalize it a little bit more. We see, but we do not observe. It is absolutely important to stop along the way and identify and observe. And when we do this, we're able to observe new implicit ideas and implications, and infer new things. And from those, we establish a new baseline. And from there, we simplify and reduce the form and abstract as much as possible without losing context. And then we generate a new set of data, and that produces results. And then we organize that and structure that data, and then we go back to step 2. And you can do this over and over and over again. It's really 6 unique steps, and the 7th step being go back. And so we have right, I'm gonna go here, I'm gonna go an algorithm research. An algorithm is just a set of steps. That's all it means. It's just a set of directions, a set of steps or directions. how to cook something. It's a set of steps. It's an algorithm. What you do in the first hour of waking up. It's probably the same thing every morning. It's an algorithm. This, an approach to analyzing, examining a topic, idea, concept in mathematics. It's an algorithm, right? And so again, what I've found is that this is not, you can do this not only in mathematics, but you can do this for a mechanical system. Your car breaks down, some part of it starts functioning. How do you do it? My trunk broke. How did I fix it? I had to take it apart. I had to take everything apart. I had to look at it. I had to observe. I had to understand how it worked. I then put it back together and then observed how it worked. I changed something. I put it back together. It didn't work. I took it apart again. I changed something else. I put it back together. I did this a couple of times, figured out the problem, understood. In the meantime, I understood how it actually worked, the entire mechanism worked, and figured out the solution to my problem. Fixed my trunk, right? I used this same set of steps. So this can be applied to physical things. This can be applied to abstract concepts. It really, you can do this in programming. You can do this for networking, anything troubleshooting, any kind of systems analysis, really. Really, an algorithm, for systems analysis. Six steps. Some have argued, ironically enough, that Alan Turing basically proposed that almost anything can be broken down into a set of 6 steps, axiomatic steps. Interestingly enough, something like that. So there we go. So this is the way that I'm going to be approaching the rest of the series. But again, I kind of wanted to make an independent, separate video for this, because this is an approach not just for the sum of divisors function, or not just for mathematics. It's actually a useful set of steps that I use in every type of systems analysis that I deal with in my life, whether it's on my job, or personally, or vocationally, or avocationally, in this case. All right, going on to the next video.